Okay, let's make a start. So we've been talking about classification, and today I'm going to be talking about features for classification, and I'm going to give the first introduction to a small part about word embedding. We'll be talking about deriving word embeddings later in the course, but I'm going to talk a little bit about using word embeddings because you may want to care about this for your project and some of the upcoming homeworks. Okay, so last week we talked, 2 days ago, we talked about classification and we talked about features that get put into the classification, and there was a number of questions about, well, what do you mean by features? And that's what I'm going to talk about today. It's like, what are the features given a particular NLP problem? What are the features that you should actually care about? Okay? Let us assume that we're going to do something like predicting the number of stars in a review. So we have a movie review, it's a bunch of sentences. Okay, each of these reviews are going to be different size, they haven't got the same number of words, they're not using the same words, they're not in the same format, they're just a bunch of random text. Okay, and they have a score of 1 to 5, the number of stars. 5 is good, 1 is bad. Okay, and what we'd like to be able to do is predict what the stars would be given the text. Okay, so we have some review and we'd like to be able to predict what 1 to 5 actually is. Okay, perfectly reasonable NLP task. There's a bunch of words. The words should in some sense be related to the score that the human actually gave, so we should be able to predict it. There's supposed to be information in these words that actually tell you about what the what the number of stars should actually be. Okay, so from the machine learning point of view, what we've got a bunch of categories, 1, 2, 3, 4, 5. Okay, I should point out that these are probably categories rather than actually a continuous score. Yeah, people might give 3.5 stars, but it's not clear that that's a linear scale. Okay, most people will give 5s or 1s. Okay, 3 probably won't get used much. There's a weird distribution of them that's not necessarily a continuous scale, so we could treat them as categories, 1 star, 2 star, 3 star, 4 star, 5 star, or we could treat them as a real number and try to do that. And that's a choice. Okay, which one's best? Depends. Okay, there's not a clear answer for that. Often you should try both. Often you should try and report to your boss the one that you predicted the best. You could have a better error if you treat them as a continuous value, but you might find it better to predict if you treat it as a discrete value. We're going to treat it as a discrete value for what we're talking about here because we're talking about classification. Okay, but that's an open question. There is not a clear answer. You might have to try both. Okay. Typically, when you're doing classification, there is a small finite number of classes that you're trying to predict. It's not 150,000 because that would be really hard to distinguish between. It's usually some fixed smaller thing, less than 100, probably less than 50, and the relationship between them may not be obvious. That's important. Okay, so it might be predicting whether this is a news story that's a business, okay, a business story, a sports story, an entertainment story. What's the distance between them? I don't know what the distance is between. They're just different categories, okay? So you'd want to treat them as discrete classes, okay? The features that you're going to use in your machine learning, whatever it is, neural, statistical, rule, must be real numbers, floats or doubles or ends, but numbers, okay, and not categories. Okay, now that's not completely true. There are some machine learning techniques which allow you to have features that have categories, most notably all of the classification regression trees and decision trees, the random forests. All of those can often deal with that, but that's only one class. For most things, and particularly neural forms, the features have to be numeric. Okay, so and we'll talk about how to deal with that if we don't have numeric values for features. How can we convert features into being numeric? And that's what we have to do. And there's often tools that will just do this for you, so you don't even have to care about it. But you have to be aware that in most of the machine learning techniques, all features have to be numeric. Okay, it can be 0 and 1. Okay, or they can be an arbitrary floating point number. They don't have to be above 0. They can be negative. They can have some interesting distributional property, and the machine learning can sort out for that. But for the most part, they have to be the same. Okay. Now, what is, I think, true for effectively all machine learning techniques, that when you're dealing with the samples, there has to be the same number of features. So if you think about being a vector of floating point numbers, the length of that vector has to be exactly the same for all samples that you're going to train from. And you might think, yeah, it's fine, that's trivial, what's the problem with that? Well, that actually causes lots of problems, okay? That especially when you've got some amount of data that you're wanting to derive features from that's of variable length. We've already said that we're dealing with some level of movie reviews, and it'll have a varied number of words. So we can't just say first column in our vector is going to be about word 1, the second column is going to be about word 2, the third column is going to be about word 3. We keep doing that. There'll only be 300-400 words at most in the review, and therefore we could do that. So how do we have this vector to be a standard size? Well, we could make it bigger than the biggest review, and we could do something like that. But that's sort of a bad idea on how to do that, because now we have some distributional property about different words near the left-hand side of our vector, and it's going to trail off as things get longer. It's not a good way to submit the information. And so we really have to come up with a way of representing our text in such a way that we have a reasonable, whatever that means, representation, vector representation that's always the same size, independent of the number of words that are in the thing that we're actually dealing with. Okay? So that's something we need to do, and I don't know of any machine learning system that can deal with a variable number of vectors. There are some that can fake it, but they do just by padding zeros on the end, okay? And that's often not ideal, because you've got to have an awful lot of data before you're going to be able to learn from it, if you're going to do the padding technique. So it's a bad idea, okay? We're having a whole bunch of movie reviews, okay, and there's going to be a number of sentences at the actual review. We're going to have a class, 1 to 5. We can deal with a class as a simple int, 1 to 5, that's at least for the first approximation, or we could represent it as a one-hot. I'll talk about that in a minute. But what do we do for the encoding the words? Do we just take the first n words and encode them and ignore everything after that? There's sometimes people do that, and sometimes that sort of works. Depending on the content of the information, it might be that all the real information is near the beginning, and the more information you get afterwards isn't that important. Possibly in movie reviews that's the case. It's definitely the case in newspaper text, okay? If you're old enough to remember what a newspaper is, or you've seen one on TV. Newspaper articles have a particular style that they do, and for the most part, the first couple of sentences of a newspaper article tells you everything. It's a summary of the whole thing, okay? It's how you write a newspaper article. It's how a newspaper article looks like. If you don't do that, then it's not a newspaper article. It's a magazine article, or it's a blog post. It's something different. But for the most part, what you get is you get a description at the beginning about the whole story, and then you get an expanded version of the story, maybe describing the characters that are involved and some background, and then you get some random background paragraphs afterwards. And the reason that newspaper articles traditionally were always written like that, and they're still written like that, even though we don't really print it on bits of paper, is these newspaper articles were usually distributed among different newspapers, and the newspapers made the decision about how much of the data they would include in the article, depending on the physical space on the piece of paper that they printed. And so most newspaper articles can be cut shorter and shorter and shorter. They still make full sense. They still give you significant amounts of information until the first paragraph. The first paragraph is really telling you the fundamental story. Okay, and so there's a style in news, and maybe there's a style in movie reviews. I don't know if people call it. The first sentence, do they say this movie sucks or this movie rocks? They might sometimes say that. Or they might save that to the end after describing how unbelievably boring the whole movie was, and at the end and say, therefore I give this a -5, or sorry, a 1 to 5. Okay, but in general in movie reviews there isn't such a style that we get in newspaper. So there's just a bunch of words, there's a bunch of sentences that may say why they hate it, they may say why they hate it at the beginning, they may say why they hate it in the end, they may leave it up to you about why they hate it. Here are the reasons for my review, and then they list things about people couldn't act, the lighting was bad, the story didn't really have any conclusions, there was plot holes all the way through it, therefore I'm giving it a 1. Nothing I said that was explicitly bad there, but these are the reasons that it are bad. Okay? So, if we're going to have a fixed number of features, here are some features that we could actually deal with. And coming up with features is one of the things that you should be aware of when you're actually trying to do one of these tasks. You can use some default features, and we'll talk about some of the typical default features, but you can also come up with new features if you feel they're worthwhile and will make a difference. And so you have to make that decision. Okay? Now, lots of other people have made similar decisions, so it's not the case that you come up with, I'm pretty sure the 4th word is the key piece of information in every review. I strongly doubt that. Okay? And that's probably not a good feature. Okay? So, one thing might be the number of words. Okay? Long reviews are probably different than short reviews. I don't know whether long reviews are more likely to be good movies or bad movies. I think long reviews are probably more likely to be good movies. Short reviews are probably more likely to be bad ones, because if you didn't like it, you're not going to spend much time writing about it. Possibly. Okay? Definitely I could believe that the distribution of everything under 20 words will be very different from everything over 400 words. Okay? So the number of words is something that actually could tell you something. Okay? The number of sentences might tell you something as well, okay? So that's not the same as the number of words because why is it not the same? It's probably correlated. So if you've got a bunch of little short sentences, okay, and lots of them, it probably means you're excited or you're not very good at writing English, okay? And if you've got big long sentences, it means you're going into lots of detail, okay? And you're writing complex sentences, probably, okay? And that probably is a different type of review. And therefore that information might be useful to a machine learning technique to try to differentiate the probability of this being a 1 or it being a 5, okay? Maybe you want the standard deviation of the length of the sentences because it tells you about whether people are consistently using short ones, consistently using long ones, or using some mix, because the standard deviation would sort of tell you not just the length, the mean number of sentences, but it might also tell you something about how varied the person was when they're writing, and there's probably information in that as well. But all of those are derived features from the data. You'd have to write a little program to be able to get that information out, and often that's a very good thing to do. Okay? The number of exclamation points in a review probably tells you something as well about how good or bad it is, and so that might be quite a good thing to do, counting the number of punctuation, and particularly exclamation points, and it's going to tell you something about it. Again, it probably tells you something extreme. It probably tells you whether it's more likely to be a 1 and a 5 rather than being in the middle. I think if somebody found a movie sort of dull and boring and nothing to say whether it was bad and nothing to say whether it was good, are probably not going to use exclamation marks. But if they thought it was the best thing ever, they might use lots of exclamation points. If they thought it was the worst thing ever, they'd probably use lots of exclamation points. So there's information in a review that contains lots of exclamation points. We could also just naively say, does it contain the word good? Or does it contain the word bad? Okay? And that's probably pretty correlated with how good the review is, and so that's quite a good thing. So particular words and their occurrence might tell you something about what their view is. So if the word good is there, it's probably a bigger chance that it's got a 5 in it for the review, and if it's got the word bad in it, it's probably got a 1 in it. Apart from, could somebody give me an example of a review with good in it that is probably not a good review?
Despite the movie's good intentions, it was a failure.
Yes. Okay, so it's got the word good in it, so yeah, it's good. But of course it immediately calls it failure afterwards, and therefore, no, it's not. So people use these words in contrast, okay? And so it doesn't necessarily mean every occurrence of the word good means it's good, okay? Because it also could have the word not immediately in front of it. This movie is not good. You go, woohoo, it's got good, so we'll give it a 5, okay? No. Likewise, you could say it's not bad, though I expected it to be. So you have to be a little careful about it. Also, there's these really weird negative uses of words, especially extreme words, such that bad apparently can mean good, okay, especially if you're Michael Jackson. You know, words like sick means bad or good depending on the context, and you've got to be the right age to understand which one it is. And so the word on its own might not tell you, but the combinations of the words actually might tell you, and you might be able to discover particular things about distributions of words if you have enough data. And that's what the machine learning's for. It's really good at that. You tell all the information about the words that appear, and the machine learning decides about the distribution of the use of those words to try to see how confident it is to be able to say it's a 1 or a 5 or somewhere in between. Okay, discrete classes. So supposing you're told in the review what the genre of the movie is, or if you're trying to classify something about newspaper reports, you know something about what subset it's actually in. How can you deal with that if you've got some discrete categories? So supposing you know it's action, comedy, romance, or something else, and you want to know which one it is, the best way to be able to do this is, well, there's 2 ways of doing this. What we could do is we could take whatever the values of that feature is and assign numbers to them, okay? And you could say that action is 1, comedy is 2, romance is 3, but the issue with that is you've now named them as a number, okay? And for example, if we're going to do something like linear regression on it, we're going to multiply that by some other number, and we're sort of got to assume that the things that are close to each other are in some sense close. So if I give you 5 different movie genres and I ask you to linearly place them on a line, okay, so we have a line from here to here, okay, and I want you to tell me where on this line of 1 to 100 action movies are and where are comedies on there. So you're going to say, I'll put actions at 83 and I'll put comedies at 27, okay. I have no idea whether that's a reasonable thing to do. And now you say, okay, romance. Where does romance go with respect to that? And it's like, I don't know, 53? There's no immediate obvious line that you could project these names onto. For the number of stars, there might be, because, you know, 5 stars, we could have number 5, and 4 stars, it could be 4, and 4.5, we could do that. But for arbitrary discrete symbols, there's not a good line that we could project these things on. So instead of doing this, we do what's called a one-hot encoding of it. And if we say there are 3 different categories, what we do is we have 3 new features, okay, 1, 2, 3, and it's really a 0, 1 on whether it's business, a 0, 1 whether it's sports, or a 0, 1 whether they're entertainment, okay? And you could do this for quite large classes, okay, and get a representation. And maybe you could even say, well, it's both sports and entertainment, okay? And so I'm going to put zeros and ones for both of those and not for business because it's not about business. Or it might be a sports story about some business thing about buying a team, and therefore you could do something like that. So you give you a little bit more control over that, but you'd have these features that you play with. But if you have that bunch of features where in general most of them are 0 and one of them is 1, it's a way to encode a discrete set of units into a binary subvector, okay, which can then be fed into your machine learning. And this is a good way to do it, okay? With really, really, really large numbers of things, it's not so good to do it because you have an awful lot of zeros in it, and that can cause problems that I'll talk about in a minute. But in general, for small things, you know, up to a few hundred, this is a perfectly reasonable way of doing it, and you can actually encode it. Now, you could try to encode it in binary within a number, but most of the machine learning things don't actually exploit that very well, even though, of course, if you put the bits in there, there are going to be ranges in the, say, int field where, you know, if it's bigger than 8 and less than 16, it's going to be business. And if it's bigger than 16, then it's going to be sport. So it could maybe do something with that. But it's typically not a good idea to do that unless you're really, really, really pushed for space, which all of the machine learning techniques hate. They always want to use all of the memory on not just the computer in front of them, but all the other ones in the rack, all the other ones in the room, and all the ones in the other company next door. Okay? You don't laugh at that, because you know it's true. So, usually having the one-hot representation is better than having just using an int number to describe the classes, unless the classes genuinely have some relative importance. Maybe if you were doing some representation of the age of the author, okay, and you had classes that are under 20, they're 20 to 30, 30 to 40, 40 to 50, then actually having a number might be a reasonable thing, because there is some notion of these ones here are bigger than these ones over here. But often there's no timeline, there's no line that makes any sense to them, and therefore it's better to use the one hot one. Okay, let's get to the words. So what we could do with the words, okay, because we could treat the words as finite classes, and we can have a big array and say I'm going to have zeros in everywhere apart from where it's that word, and so somewhere in the middle of there's going to be, for the word good, I'm going to go 1 and everything else would be 0. You could do that, and that's actually what we do. It's a way of encoding words, but in order to do that, you have to first decide on your vocabulary, okay? Because it's got to be a fixed length, so you've got to decide on your fixed length vocabulary, and whatever you decide on your fixed length vocabulary, there's going to be another word which is not one of those words, okay? So when you're encoding the review and looking at the words in the review and looking at word number 1, word number 2, word number 3, yeah, it's great. And then you get word number 4 and it's Nebuchadnezzar, and you don't have a space for Nebuchadnezzar. It then becomes other, gets the 1, okay? Deciding on you could make it 0 and 1, whether the word appears. You could also make it 0 or the number of times the word appears. But realistically, 0 and 1 gives you most of the information. You might think that's a little weird, but it isn't, okay? Because actually, it's not the ones that are telling you lots of information. The zeros are telling you lots of information. And so if you find out about a bunch of words that are there, it sort of doesn't really matter whether they happen a lot of times or whether they happen more than once. Being more than once, more than 0 times is actually much more important, okay? But, you know, you have to test it. Now, what do you do about that vocabulary? So, you clearly have to have a corpus of the words that you actually care about, okay, within your reviews, okay? And so if you've got a training set, you go and look at all the words in the training set, you probably calculate the frequency of each of these words, and you look at the tail of how the words are actually occurring. And what you'll probably find is about 45% of the words appear once and only once. In natural language distributions that are usually Zipfian, in natural language, the way that curve actually happens is usually it's about 45% appear only once. Okay, if you discover that 98% of your words appear once, you're probably doing something wrong. Like you've accidentally included some header information that's got an arbitrary number in it, which was guaranteed to be unique, and therefore you get a lot more unique things than what you would normally get in natural language. But you're going to get this distribution, and the is going to be way at the top. Okay, it's going to appear about 4% of the time, and Nebuchadnezzar's not going to appear, but a whole bunch of words, almost half of them will appear once. Okay, and only once. So that means in all of your reviews, that word appears once, and only once. And that's going to be very hard for that word to mean anything, or you to learn anything from the occurrence of that word. You have zero contrasting information about it. Maybe you could find out that if that word appears in this review, you know it's a 4, and therefore I'll just do that. So I could sort of encode that information, that when Nebuchadnezzar appears, I know it's a 4, and I don't have to look at the rest of the content of the words. But in general, the ones that appear once, they're not giving you much information in an information theoretic sense, and so maybe you don't want those. Okay? That will about half the size of your vocabulary, so all of a sudden everything gets a lot shorter, and that might be a good thing to do. Okay? You maybe want to test that, because it's not always true, but it's something that you could actually consider. Okay? Do you really want to care about the number of occurrences of the word the? Okay? It will almost always appear unless the thing is very short. Okay? Yes, you can write whole essays without the in them, but it's hard to do, okay? And most people won't. So there'll be some exceptions, but in general, the will appear everywhere, so maybe you don't care. But realistically, the things that appear a lot are all going to be in the top 50, and why not keep them, okay? There's sort of no, it doesn't really matter, probably, okay? Because they'll mostly appear everywhere. And in fact, when they don't appear, it probably tells you more about the length of the review than the content of the review. Possibly what you could do is only look at the relevant words in your domain, if you had them. Okay? If you knew something about the domain that you're looking at, you could actually exclude everything apart from the important words in your domain. Imagine what you wanted to do was you wanted to look at reviews of movies, and you wanted to find overall the most popular review, the popular movies. What you could do is say, I only care about occurrence of words that are in movie titles, and I won't care about any of the other words. And so you could build your word frequency information out of movie titles rather than review words. You could do something like that, and sometimes that's a good thing to do. Okay? So instead of having all possible words, you only have only the interesting words. So imagine that you were going to build something from Stack Exchange, and you were going to do something about C++ or some standard library, and you wanted to know about who's talking about what functions. What you could do is you could say, I'm only going to care about the names of the objects that I know are in the library. I don't care about the rest of the words. Okay? So you could do something like that. So they're not really English words, but they are words that really mean something. And yes, there's probably some that are confusable, but you could do something like that. And that would be a reasonable thing to consider. Okay? This vector that you get to represent the words, the longer it is, okay, the sort of harder it is to train. So you'd like to make it as short as possible, but the shorter you make it, the information you're losing. So there's some optimal size, and you don't really know what that is, okay? And without testing, I don't think you can sort of predict it. But it's not unusual that people are dealing with vectors of 1,000 or even 10,000 or even 100,000. Though you probably need an awful lot of data when you're dealing with vocabularies of 100,000. This vector is going to be mostly zeros, okay? And it's going to take up an awful lot of space in your computer. You're going to say, why? I've got a big computer. But if you've got 10 million reviews, and you're going to represent each of the words, and there's 400 words on average in every review, and each of those is going to be represented by 100,000 floats, okay? All of a sudden your computer is not as big as what the guy in the Apple shop was telling you, okay? And you'll run out of space, okay? Well, you won't, because it'll be on disk, and we all know we have an infinite amount of disk space, but the time for processing actually is non-trivial. So there's some trade-off there that you want to actually care about, and maybe you want to care about really efficient representations of very large arrays with lots of zeros in them. There's a whole bunch of implementations. If you look on Python or Java, there's a bunch of implementations that allow you to do this. Or you might actually want to find another way to represent the information so you can collapse it, okay? Because this is not the most efficient way of holding the information. This big array of looking at the words, and particularly in saying, here's my representation of the first word, my second word, the third word, and if I put them all together into one big array, so what I have is, for every time a word appears in the whole article, I put a 1, and when the word doesn't appear, it will get a 0. So we'll end up with a few ones. Let's say on average if we have 400 words, but some of these words will repeat, so there might be 150 unique words in the whole article. We'll get 150 ones, and the rest of the 10,000 will be zeros. That big vector, that way of representing the information, is often referred to as a bag of words, okay? It's called a bag of words because we've lost the information about the ordering of the words, and we only know which words appear. So it's like, I take the article and we pretend that they're all a bunch of Scrabble tiles, okay? And what we do is we take, oh no, Scrabble tiles would be letters, but individual words, and then we put them in a bag and we sort unique them, so we've only got one of them. We just have a bag of random words. We have no idea about what the order is. There is an awful lot of information that's in there, and in fact, for many natural language processing tasks, that's sufficient, okay? You don't actually have to care about the order. There's enough information in just the bag of words that will get you incredibly far in natural language processing, okay? It doesn't always get you all the way, but you know, it gets you a surprising amount of way. And so often when you're trying something, you go, well, we'll try the bag of words thing first and see whether it makes any difference at all, and then we'll use that as a baseline and see if we can get better than that, okay? So the bag of words does not care about the word order, so we've lost the information that even though the word not appeared, we don't know what appeared immediately after it, so we can't cancel that information out. We don't care about the number of occurrences of the word. Theoretically, we could have 4% of them being the word the, and then the rest of them, but usually we do not do that. But much more importantly, we've now got a standardized vector that's the same length, independent of the number of words that are in the review. And now we can start doing machine learning with it. So this is the big thing that you get out of bag of words, is we've now got a fixed length, review length independent representation of all the words with zeros and ones in them, but we know it's always the same size no matter the size of the particular review. The longer the review, the more ones there are going to be in it, but you know, it's never going to get bigger than that size. And that's a good thing to have, and it's something that's pretty much necessary when we're actually trying to do machine learning. Right, so now we have this big vector. I'd sort of like to know whether this big vector for review number 1 and this big vector from review number 17 are similar or not. So we could subtract them, okay, and find out the overlap of words, because that's what they would do. You treat it as a very big number, and we just subtract them, and every time they're different, we get a number. When they're the same, they'll be 0. So if they're both 0 or they're both 1, they're going to agree, but when they're different, we're going to have some information about that, and that would tell us something. And the closer they are, probably the more similar they are. Okay? We don't know the thresholds of what real similarity actually is, and yeah, there could be a really clever review that's got exactly the same words, but the words are jumbled in a different way, and this one's negative and this one's positive, but most of the time that's not going to happen. If these two things are somewhat similar in distribution, they've probably got a similar review, probably, okay? So we can do simple difference, we can do edit distance, not different, distance, which is sort of the same thing. Or we can do cosine similarity, which is actually treating it as a vector in n-dimensional space and looking at the angle it is. It's almost the same thing as well, but especially if you have things that are counting the occurrence of words, it will do that slightly better. What we've got in this model is the person says in the very simple review, I love the film, okay, it's going to be equally different from I hate the film and I like the film. And we probably think that if it says I like the film, that's closer to I love the film, and that I hate the film is really very different, probably. But the distance metric, if it's looking at word distribution, okay, is not going to be able to tell, all it's going to be able to tell is there was one word different, okay? And it's 0 or 1 no matter what the word is. And there's something about the word love and like that makes them closer to each other than hate, okay? Dislike is maybe closer to hate, but we'd like something that doesn't give 0 or 1 for being different words, but actually could give you some number about how close the words are in meaning, something like that. Okay. But there's another aspect of the closeness of words, is we actually might want to care about the context that these words are in, because the context these words are in may also give something. So again, we've got this film is good, this film is not good, this film is very good. And all we have is one word insertion, okay? But it makes it either very good or very bad, okay? And so this is not just a word choice thing and not just a distance metric. There's something about, I'd like to know the context of these words as well. So there's two things. One is, for a particular word I'd like to care about is distance metric, and there's also something about context that I'd like to be able to capture in order to be able to distinguish things like this rather than things like just simple word replacement. Here we've got word insertion, but they push it in different directions. Okay. So word similarity, we'd like to, rather than have a binary representation of 0, 1, we'd like to be able to get some distance metric, so we'd like to know which words are close to each other and which words are far apart from each other. Now, I could ask you, okay, let's do something like colours, okay? And so I'm going to ask you about colour words, and I'm going to give you 3 colours. I'm going to give you yellow, blue and turquoise. May I first apologise to all the men in the audience who've only got 3 colours anyway and don't care. I saw somebody else give this example, this is why I'm doing it. So we've got yellow, blue and turquoise. Okay, so let's talk about yellow and blue, and I'm now going to take the word turquoise. Is turquoise nearer blue or nearer yellow? Hands up if you think it's nearer blue. Okay, hands up if you think it's nearer yellow. Hands up if you think it's nearer green. Yes, cultural difference. These things are hard, but we have some agreement on that. Okay, what about chair, table and honesty? Okay, so I've got chair over here, I've got honesty over here, and I've now got the word table. Where do I put it on this timeline between chair and honesty? Do you think table is closer to the word chair? Do you think table is closer to the word honesty? Oh, wait, I didn't give you an option to say nothing, but yeah, so, but we've got to project them on the timeline and we've got to get a number, okay? The answer typically is people are pretty good at telling you about distance metrics when they're really close, when there's an obvious relationship, okay? And they're utterly useless. I thought you would get chair and table together. I have another example where I was going to take much more abstract things and see if you could actually give, you know, Nebuchadnezzar honesty and I don't know, that's just something that's not connected to any of those. Insects, okay? And what's the distance metric between all of those? And the answer is Well, clearly 2.7 to the power 17 for the first one. And I mean, no, there's no sensible number distance between these things. We don't think about things like that. But if we make the machine do it, it sort of has to do it. Okay? And it will, because we asked it to do it, because it doesn't do what we don't ask, but it doesn't always do it in a useful way. And so close distances probably mean things, long distances are probably don't really mean anything. We're going to do a lecture later on where we're going to talk much more about deriving these numbers. For the moment, what I'm going to do is I'm going to say, you can download a Python library and it will do it for you. Because that's often the answer to everything in the world. There's probably a Python library that does it. Okay? And if you're a little bit older than that, there's a Java library that does it for you. So don't worry about it. So, but we'd like a distance metric that would allow us to try to do that. Now that's one thing. Given a word and another word, I like to get a distance metric, and I like something to know whether they're more similar or more apart. And realistically, I don't care about a really whole floating point. I probably care about only being, it's relatively close or it's nowhere near. Really, that often what it is. But you know, it's exactly the same, it's somewhere near, it's somewhere really, really far away. We don't actually need much distance there, but we like to have. The other thing is the context. Okay, I'd like to know that whether the occurrence of the word good and the occurrence of the bigram not good, they really don't mean the same thing. And I'd like to push their distance further apart. Okay, so when not good appears, that's really very different from good. Okay, now there's other things like pretty good. Depending on which country you grew up in, you might think that's near good, or you might think it's nowhere near good. It depends on maybe even how it's said, but it still seems to be much better than not good. Okay, but you know, if it's Nebuchadnezzar good, I don't even know what that means. Okay, if it's chocolate good, it probably means it's good. If you think chocolate is good, if you don't, then that's not going to work. So there's a couple of things that people do to try to make this work. One of the things that you do, we talked about having a vector of zeros and ones for all the words, okay? We could talk about a vector of having 0 and 1s for all of the bigrams that appear in the data, okay? Remember I said that you'd run out of memory if you had a big vector for all of the words? How big do you think the bigram vector is going to be? It's going to be, you know, the number of words in your vocabulary squared, which at 10,000 is going to be very big, and at 100,000 is going to run out of memory. So it's maybe not ideal, but you could look to see which bigrams appear in your data, which won't be anywhere near all of them, and then you could only care about those, and so you could try to encode some more information for that. Okay, and that would be reasonable. Okay, it probably only be about 5 to 10 times bigger than your original one, and you get some contextualized information. Yeah, so we talked about like and love being more similar than like and hate. Now, we also talked about representation of being the sparse form of mostly zeros with the occasional one. And that's what's called the sparse representation. But we can get dense representations, okay? What we could do is we could try to hash these really big things into a much smaller number, okay? So instead of having 10,000 floating point numbers to represent the information where there's only one 1, what we could do is we could try to find ways of hashing that information into some hash table that would then give us a bunch of things that would be treated as similar with only 100 numbers to do it, or maybe even 20 numbers to do it, okay? We'd have to get the right hashing function to do that, so we want things that are somewhat similar, and so what we'd really like to know is, here's 2 words, okay? Should they be in the same group or not? Would that be a good thing to do? So, for example, they're all colours. It might be a reasonable thing to dump together because they're sort of all colours. Yeah, they're different types of colours, but you know, they're all colours. It makes them very, very different from, you know, king names from Europe from 500 years ago. They're a different space. Okay, so we could do that, and that would be a reasonable thing to do. Does anybody have any ideas of how we might be able to detect whether words are in the same class or not automatically? So words are sort sort of dependent on the context they're in. And so often if you get words of the same class, they end up appearing in the same context. So I happen to say, you know, kings of Europe from 500 years ago, they will often have the word king in front of them, okay? So what we could do is we could say, here's a couple of kings, okay? And so we get the Edwards and the James and the Louis the 14th, and we find that, and we find all the other ones that have got the same context as Edward, James, and Louis the 14th, and look at all the names that actually appear, and then we'll get northern, southern ones, we'll get Latin pronunciations, and we'll get Romance, and we'll get Germanic pronunciations of them all, and then we'll be able to find that here's a bunch of words that appear in sort of the same context, okay? Likewise with colours, what we discover is colours actually end up being in a very similar occurrence, so we get to discover that, you know, they'll often appear in lists of 3 or 4, so this jacket is available in red, pink and other, which then becomes a colour, but other is sort of a colour at some level. But you discover that the names for colours often appear near other names for colours, and there are ways, to, and we'll talk about this more later in the semester, of trying to discover classes which are similar. So in other words, if we know the 3 words before and the 3 words afterwards for every word, what we can do is we could say, okay, let's actually look at the word and find everything that's got the same 3-word context. Well, maybe not the same actual 3-word context, but where they've got approximately the same 3-word context, and find the most common context that've got different words in them, okay, and say they're in the same class. It sort of works and finds classes for things that work. So we could do that, and we could do some way of trying to put things into classes and reduce it. And again, we'll talk about this a little bit later. When we talked about part of speech tagging, did you get told about brown clustering? Anybody remember the term brown clustering? It's on one of the late slides in one of the lectures, and I think it happened, although I didn't do it this year. And brown clustering is a technique for looking at a big data set and trying to find effectively who's got the most common context, okay? And so it tells you to actually put things together. Brown is not because of the colour, it's because of the guy that did it, Peter Brown, who actually did that at the end. In the dense form, okay, so suppose we don't have 10,000, we have 100, we'd sort of quite like each of these numbers in the vector to mean something, okay? We're always happy when things mean something, but when you ask somebody, what do you mean by meaning, nobody has a good answer to that. But it would be nice if, like, the first one said something like, it's a name of someone, okay? And the second one tells you about whether it's abstract or not. The third one maybe tells you whether it's a place. The third one, and so it would be nice if we had that, but that's actually incredibly hard to do. We can do that post hoc. No, we can do that explicitly. So what we can do is look at all the data, find all the names, label them with a little prefix to say that this one's a name, and by some named entity labeling, and then use that information in the encoding. And that's often a good thing to do if you can do it. We'd like our representation to have a distance metric that was useful. So if we did a subtraction between them or cosine similarity, they are more similar. And if the number is big, then they're less similar. We'd like that to be true. And we could try to do that in the way we actually try to generate these things. People talk about word embeddings, the dense representation, as saying they have meaning. That's completely false. They do not have meaning. They're typically representing the context that the word most likely appears in, because that's how they're derived. Okay? And but there's a bunch of numbers in there, and we don't really know what they represent. There are, you'll be pleased to hear, a whole bunch of standard embedding libraries out there, and they've got various properties that make them good or bad. The most common one and the most famous one that started it all off, actually didn't really start it off, but it's definitely the most famous one, is Google's Word2Vec. It started in 2013. You might even have seen things about Word2Vec. Word2Vec does, in its paper, make some claims about meaning. They discovered that if you took the representation for king and you subtracted the representation for male from it and added the representation for female, you ended up with something that was close to queen. You think, that's pretty cool, okay? But actually, when you start doing really interesting tests on that, it's not as obvious. So don't always believe that. But Word2Vec is pretty good. It gives 300 floating point numbers as a vector for each word. There's a big table, you can go look it up. You can look it up online, and it's got millions of words in it. You can get a download version that's in Python that's only got a few 100,000 in it that are the most frequent words, and you get something for the unknown word, and it gives you a representation. It's pretty good. Okay. It was derived by a neural autoencoder that we'll talk about again later on. Did we talk about that? Yeah, we do talk about that later on, where basically we're trying to discover through a neural net a 300 representation for the 100,000 representation for the words. GloVe comes out of Stanford, and much to people's surprise, it's nothing to do with neural nets at all, although everybody thinks it's a competitor to Word2Vec. It has to come from neural nets, but no, it's analytically derived from the context of the words that are actually in there, and ends up using something like PCA to be able to reduce things. Again, looking at context to be able to do it. Often GloVe is better than Word2Vec. People are not really sure of when it's better, but it often is, and so you can try that. More recently, there's been two ones for a bunch of people who are just the right age to have watched Sesame Street when they were kids, and they are called Elmo and Bert. And Bert is, I have another slide on Bert, so we'll come to that in a minute. They're better in general. They care about the context, so if you've got a word, you can't look it up the Bert representation in isolation. Well, you can, but that's not what you should do. You should look at it in the context of the sentence that it's in. And therefore you get a different representation for the word apple in Apple Inc. stock went up yesterday, as opposed to I picked an apple from the tree. These apples are different, okay? Because one's talking about the company, one's talking about the fruit. But in GloVe and Word2Vec, you get the same representation that might have the dual meaning of company and fruit, but you get actual different representations, and that often gives you a better representation of Bert and Elmo. You can train your own. So you can train your own representations. So what you can do is you can take a corpus, and you can try and get the best 300 floating point numbers to represent the words that are in your corpus. That's sometimes really good to do, because then it cares about the language that is in your corpus. And if you've got a particular type of language, even though it's English, but it's some subset of English, for example, it's computer speak, so it's from Stack Exchange, and therefore it's got lots of funny things that are not in standard English, or it's medical speak, or it's Twitter, which isn't English at all. It can be a lot better to be able to build your own. However, you need lots and 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 lots of examples to be able to do that. And often you don't. Sometimes you do. If it's a very particular language, okay, you don't need so much data to be able to train. So, for example, if it was going to be air traffic control speak, which is actually pretty restricted and actually is a legal definition, but you can say other things in it as well. You're allowed to ask what the score is in the football game. But I think that's actually explicitly in the list. But most of the time it's very, very fixed vocabulary about what you can say with various numbers and directions and things. Actually, you probably want to train your own because it's so specialized, it's probably a better thing to do. Skipgram's another toolkit that allows you to be able to do that. Okay? When you're considering that, what you have to consider is my data like standard English? So you really want to know what was standard Word2Vec, GloVe, and Bert trained on, and is my language a subset of that, and a reasonable subset of that? So if you're doing movie reviews, it probably is. Movie reviews are going to be a little bit more personal than Wikipedia and news stories, but it's still going to be sort of the same thing, okay? If your data is going to be something like interactive dialogue, then it's not so clear, okay? Because interactive dialogue has got a very different distribution of, for example, I, okay, the first person singular. In dialogue, it appears all the time, okay? While in newspapers, it's surprisingly rare, and in Wikipedia, it's much more rare. You might think, wait, why is that? Well, because when you're talking about yourself in your interaction, you talk about yourself. But, you know, most things that are written in newspapers are written in the past tense, so you don't get is very often. And you get occasional quotes saying, you know, I am something. But most of the time, you don't. It's got a different distribution of the type of sentences. So it's something to consider, okay? So is your data special or not? And that's something you have to consider, okay? Exactly what we mean by special is not clear, but, you know, if it is standard text or almost standard text, probably you don't need to retrain. There's no point in doing that, okay? Do you have enough examples, okay? You've got to have hundreds of thousands of examples before it's going to train, okay? So if you've got, you know, 100 dialogues, it's not going to train, okay? Unless, say, a traffic control speak, which is really, really fixed grammar, for the most part, apart from this. The other thing is, do you have a bunch of very standard words that have a very different meaning within the domain that you're in, okay? And that's often not hard to follow. For something like, so it's okay if you have a few words that are like this. I used to be on a network mailing list, and within networks there's a thing called named, which actually does your DNS for you, but it's written as the word named, N-A-M-E-D, but it's namedy because it's a daemon for running names, okay? And everybody knows that, but it looks like the word named, and it's not the word named, it's actually got a special meaning. And so if you have lots of things like that that are confusable, it can really break things, okay? And so you have to be aware of what your domain is, whether you need to train your own embeddings or not. How long should your dense vector be, okay? Somebody asked me that last week, and the answer is, nobody has a clue, okay? People will make arbitrary claims about it's very clear that this is better, but nobody has investigated all possible sizes. And I don't think there is an answer, because it depends on the task you're actually doing. It used to be, before we got Bert and Elmo, everything was 300, and if you tried to find out why it was 300, the best story was, which may not be true, but it's a good story, so I'm going to tell you, and that is, that's what fitted in the GPU. Okay, it's not a good answer, okay, but that was the largest they could get in the GPU for all the tests that they were doing, so they had 300. And 300 is an awful lot of numbers, so if you think about 300 floating point numbers, and you think about the number of possible numbers you can hold in 300 floating point numbers, it's more than the number of particles in the universe, okay? So it's a lot. So if you imagine that it was representing different states in the universe, well, okay, so we then have to care about all the possible places where the particles are in the universe over the last 13.4 billion years, and the answer is, yeah, you can do that in 300 floating point numbers. I've not done it, so I don't actually know if that's true, but it's an awful big representation, okay? But that's not the point about whether you could compress all possible states into that. It's whether it's a useful representation. And maybe what you want is you want some of these numbers to actually mean something in the n-dimensional space and not just be arbitrary. And so that's why people start looking at bigger ones, because then maybe you can get a better representation that allows it to know that automatically discovers that position 37 in the vector is a really good thing talking about physical size, okay? Because it happens to be correlated with that. And then you can have things that just look at number 37 and be able to work things out about it. Now, it might not be as simple and as obvious as that, but the wider you make it, the more likely there could be classes to do that, probably, if you could train it. Nowadays with BERT, it's 768 or 1,000. So it should be 1,024, but I think it is 1,000. So clearly they changed their mind what they're getting at. But it means it's still very big and it fills up your GPU very quickly. So the thing about getting the dimensions which are useful, okay, in some definition of useful, does it train better? Does it solve my problems better? Is really what it comes down to. It's pretty hard to implicitly understand what the vectors are. I don't think anybody really does that. There are some people who try to manipulate the space of what these things are and try to force them to have things in it by actually, as part of the training. But it's pretty easy to explicitly do it. Okay, so for example, I mentioned earlier, maybe what you could do is you could put an extra floating point in the beginning that identifies the class of the word that you're actually dealing with. Is it a place name? Is it a person name? Is it an action? Is it a function word? That sort of information, it's pretty easy to explicitly do, and it's sometimes incredibly useful in training because very quickly you're giving it known useful linguistic classes and it can make all of your training much faster. It doesn't always do that, but sometimes it does. Or you could actually say, I'm going to represent a word not just by its 300 floating point numbers. What I'm going to do is I'm going to represent it with the 300 floating point numbers, then I'm going to represent it with 40 numbers to identify its part of speech, and then I'm going to actually represent another 300 words that represents its head in the syntactic tree, so the word that appears above it in our dependency grammar, or the word that appears before it, okay, or some other piece of information. So you're explicitly giving structure to the representation of your word. And that sort of technique often works very well. There's an infinite space to search for that, because it can make it quite hard, but that type of extra information can often really help. Okay. Another thing is there are new embedding techniques, word embedding techniques that come out almost every day. In fact, probably since I started lecturing this at the beginning at 3 o'clock, there's 4 on archive that are already out there. And maybe being a little bit facetious that they're coming out early, but they do come out pretty quickly, and sometimes they're drastically better than the previous one. Okay? And this has happened a number of times in the last 5 years, so it's very hard for me to write a slide and go, here's the best possible thing on the planet, because by the time you do your homework in 2 weeks' time, I'm wrong. Okay? Usually, I'm not very wrong, I'm just a little bit wrong, in that the thing that I say at this time is true, and the new one is maybe better than the current one, but this one doesn't get worse. So it's probably okay. Word-to-vec and glove are pretty standard. It's sort of, if you're trying to get more meaning, glove is sometimes a little better, but word-to-vec they're not wrong, and they're perfectly reasonable and very easy to do, and they have Python libraries, and people have been using them for 5 years. It's just great. It's probably the easiest thing to do. And if you're going to train your own, they're the easiest ones to train, because you don't need an infinite amount of data to do them. Okay? Then last November, there was a paper that appeared on archive from Google that was the system BERT. BERT stands for something, but I don't think anybody knows what it stands for. And I did look it up this morning, and I can't even remember. But almost everybody in NLP knows what BERT is. In November, they published a thing on archive, and they said, here's another way of doing embeddings. I'm not going to go into all the detail about it, but the thing that was important about it is you get a different representation depending on the context that the word is in. So instead of you just look up the single word and get a representation, what you give is the sentence, and then you get the word representations for each of the words in the sentence. And it's true that the word apple in Apple Inc. stock went up, and I picked an apple, will be in some sense similar, but it's also true that they're different because they have a different meaning. But it's caring a little bit more about the context. And the people who did BERT, what they did was they tested how well it solved 11 different standard NLP tasks. And this was things like sentiment, question answering, named entity recognition, and they were all better than anybody else who'd done any of these things on the planet. Okay? So all of a sudden people said, whoa, BERT is the most interesting thing and is better than anything else. Hence the little phrase, everything is better with BERT, okay? It's not actually true. There are a few things that are not better than BERT, but it's sort of a good takeaway. And the conference that that paper was officially published at, so it was released in Archive, which is not an official publication, but it came out in NACL last year in June. At that conference, I asked somebody, I didn't go to it myself, what was the feeling of the papers, and they said everything is better with BERT. Almost every paper was about, here's my task, I used BERT, it was better. Okay, so it's really pretty interesting that we could have something that's drastically better than that when people have been working on this, when people have an infinite number of data and an infinite number of GPUs, but Google has more than the rest of us, and so they were able to do that. And in their paper they actually say, you know, we weren't very sure of the best way to do this, so there's lots of different choices of doing the contextualized information, and we chose one of them. And we trained it for like a week, and we got this thing that was just much better, and so we're very happy about it. But we're pretty sure there are also better ways of doing sort of the same thing. And there was a paper here from CMU recently called XLNet, a student in, two students, sorry, in LTI, and they got something that was again better than everything that BERT had done. They don't have an online thing that allows you to run to be able to get the embeddings out of them, so it's a little harder to use. And BERT is still better than everything else, but XLNet, especially as a CMU thing particularly, is better. So BERT embeddings are probably the best. However, you should be aware that for the particular task you're doing, BERT embeddings are really big. And so they might be overkill for what you're doing, and therefore not worth it. And it might be that Word2Vec and BERT are about the same, and Word2Vec will train in time for the homework deadline, which is in 2 hours. I'm joking that it's in 2 hours, and that you'll be doing it 2 hours before, but you know what I mean, okay? Okay, so we've now got these wonderful embeddings, dense representations for words that have some notion of a distance metric that means something about the meaning of the word. This is cool. Let's go back to our problem of trying to work out how to do prediction, the number of stars given the review, and so for every single word we've now got a BERT representation. How do we use it? Well, remember, we've still got a different number of words depending on the review that we're doing, so somehow we have to take these embeddings and join them together into something, okay? So there's a number of ways of doing that. Something utterly ridiculous, like you add them all up. It works. Okay, it sort of shouldn't work, and I remember when we first tried it as a baseline we were convinced it wouldn't. You can take the average, because if you add them all up, the number of the magnitudes are going to be bigger for the things that have got more words in them. So you take the average of them, and it sort of works, okay? And for a first approximation, it's not as stupid as what it sounds, which means that the individual vector, the individual values in the vectors have got something to do with dimensionality that are orthogonal to each other, even though that's not explicit in the training. The other thing that people do is what's called max pooling, and so what you do is you look at all of the words through it and you find the maximum number in the 0 position in the vector, the maximum number in the 1 position, the maximum number in the 2, and that seems to work as well, and is sometimes better. Okay? Now, of course, that's a quick way of doing it. The better way to do it is to try to take the sequence and try to predict another vector that takes into account the important information that's in there. And that's often what we do. We'll do some form of sequence LSTM model to get a representation of the sentence that typically would allow us to reconstruct the sentence. Okay? The other thing you could do is you could build a BERT for documents. So what you could do is you could take all possible documents on the planet and try and get a representation for them, caring about the context that the document is in. Now, although theoretically that's a really good thing to do, you have to understand something about the distribution of words and sentences in the world. Okay? We have an almost finite number of sentences. Okay? The number of words. You know, we can deal with 1 million words, and if we were banned from using anything new apart from that million, we could probably survive apart from Californian startups who want cool names to have for their company. But apart from them, we could actually deal with that properly. Given the number of words, if we talk about the number of sentences in the world, there's a lot more sentences than there are words in the world. It's not the number of sentences to the power average number of words. It's not that, because not all combinations of words make sentences. But it's really, really big. And what makes it even harder is people like to come up with new sentences that have never been said before. It's sort of their job. And in fact, let's be even more specific. The sentences that have never been said before are the most interesting sentences. So we tend to focus on the new sentences that we've never seen before. And therefore, it makes it much harder to try to train something where all of the interesting new sentences that we might want to encode after we've trained our system will be things we've absolutely never seen before. And what's more, they have a meaning that we've never seen before. With words, most of the words that we use have the same meaning that they had before. Okay, yeah, there's drift in meaning in words, but for the most part, words are relatively fixed in their meaning, but sentences will have different meanings. There are sentences that mean the same thing, but there'll be new sentences that also mean that later, and might even change meaning over time. So trying to get an embedding for whole sentences, or even whole documents, which are longer, might not be possible. Now, I don't know if there's a proof to show that, but it's definitely something that is orders of magnitude harder than trying to get a representation for words. And so you should be aware of that, okay? Which means, in general, that trying to get a representation for sentences and documents is probably not possible, and it might be something that you really want to train for your particular domain, because your domain is going to be a subset of the world, and that's the thing that you care about, and you don't care about obscure physics journals when you're actually trying to do reviews for movies, probably. Okay? So getting a representation for documents is still sort of an open problem, but there are quite good ways of doing it built on top of BERT, and BERT did win 11 state-of-the-art things in their paper. There are an awful lot of words, okay, and so it's always good to try to reduce the number of words, because not all of them are interesting, and not all of the distinctions between them are interesting. So contextualized word embeddings try to address some of that, so they're encoding something about the thing round about it. Having to include the bigrams in your vector representations makes things big really, really quickly. And so it's good to avoid that. You could still just concatenate the previous and next word onto the current word, and you've now got a representation that's 3 times the size, but it has some contextualized information in it. That will probably be a good way of doing it. You probably want to care about case folding. We mentioned this before, but you know, upper and lower case has got meaning in English, but most of the time it doesn't, and it's a good way to reduce things, because there's lots of confusion about often when uppercase is used, there is no difference in meaning, and so therefore flattening it will give you a bigger gain than the information that you probably are going to lose for that. Part of speech is wonderful. This is why we have part of speech. Part of speech is a way to try to normalize things out about the meaning and care about the syntax, and give us another representation that's much more compact, because there's only 45-ish different part of speech tags, depending how you count. And therefore, if you have a representation of the sentence of part of speech tags, you may actually end up with a better and more useful representation in dealing with the words. Or you use that and only the most unusual words in the document, the words that don't appear in other documents, which might be telling you most about it. Okay? Also part of speech tags, because there's less tags, there's less contexts, because the maximum number of contexts is the number of words times the number of words times the number of words if you're doing a trigram representation, where if you've got 1 million words that gets big really quickly, but if you've only got 45, it's 45 times 45 times 45, which anybody who's still awake will be able to tell me the number is about 71,000, I think. So it's easier, and many of them don't exist. Many of them are so rare that you don't actually have to worry about it. What happens when you get too many features? So we've got this vector of features we're going to stuff into it. Then you've got to begin to get careful. So if you give it 1 million features, you can pretty much guarantee that for a particular sample, there's some unique features that appear in that sample and nowhere else. And if your machine learning is really good, it will find what the unique features are, it will remember the unique features, and then try to predict the class based on those unique features. That's useless to you. Well, you get a really high result on your training data, but you get utterly useless results on your test data, unless it happens to be exactly the same as one of the things in your training data. Okay? This is what's called overtraining, so it doesn't have to be exactly the features, but a large number of them. But the more features you have, the more likely you're going to be able to learn some pattern that's not the pattern you'd like to generalize. Okay? So you don't, although more features usually helps, more features also have the problem of overtraining. Okay? How many features? Don't know the answer to that. It's really hard to even give a rough idea about that. Usually 2 or more features or 2 less features are irrelevant, unless you start off with 2. Doubling or halving can make a big difference. Find a way to reduce the features so that you still contain the same information is a perfectly reasonable thing to think about doing. What I'd like you to do when you're thinking about features is you should think about the features. Okay? What are the features that would help solve the problem? Okay? What features do you use when you're reading a review, when you're trying to guess what the number of stars are for the review? Okay? Do you look at how knowledgeable the person is about the movie? Did they quote things? Do you think that makes it higher or less? So should you care about getting a feature to know whether it's got quotes in it or not? Probably. That would probably make a difference. Okay? Imagine you wanted to detect whether the author of the article was male or female. Okay? There's this really interesting thing about we would like there to be equal numbers of male and female in everything that we do. Actually 51% to 49% female to male. But actually in many cases it is illegal for us to ask people what their gender is. Yet we're still legally required to identify that we have an equal distribution of gender. So how can we do it? Well, we can build a model that tries to estimate what gender is, and so we can look at examples and then try to guess what it is, and then for some very small subset, we can actually get the information with permission and be able to work out whether it's true or not. So imagine that you had to do this task, and there are lots of people having to do it, to check that there's not biasness in systems, and you're going to say, not work out whether the review is 1 to 5, you're going to work out whether the author is male or female. For the most part, there is no difference in writing, so there's going to be a whole class that you cannot identify. But in English, there is a different distribution of words that women use as opposed to men. Okay? And you can find this in data. Okay? Now, in some other languages, there's explicit grammatical forms that are used by women and not used by men, and the reverse. So it can become an easier task. In Japanese, the first person personal pronoun, the one that means I, there's a whole lot of them, and a lot of them are very gender directed. Okay, there are sometimes where you can do a different one, and there's polite ones which are gender free, but there's still a very strong information about who the gender of the speaker is on the way that they're actually doing on the words, much more than English. But you could try to do that, but you could try to think about which words in English, okay, are more likely to appear in an article written by a woman compared to written by a man. Okay? Now, you might be thinking about, so there are things like, you know, what's the example? Gorgeous. Gorgeous is supposed to be a word that's used by women and not men in English. That's probably not true anymore, because there was a pop song a number of years ago, You Were Gorgeous, and therefore everybody started using it, so it broke it, which is a good thing. But there are other things that will do that. The use of the word my husband, okay, will probably infer that the person's more likely to be female than male. Yes, there are male people with husbands, but there's substantially less of them, okay? And so there's certain things like that that will, and so you have to think about when you're solving a problem, what is the information that I need to ensure that is in the system, that the system can make the decisions about the thresholds. It's really good at doing that. Okay? Oh yes, summary. Features must be numeric apart from some really special cases, so you should always think about that. You can convert discrete features into one-hot ones. Sparse versus dense word representation, so you can have this big bunch of zeros and ones, or you can get the representation for word embeddings. Bag of words is a really good start for almost everything that we do. It really works pretty well for many things. Word embeddings, which are a dense representation, they can be pre-trained or trained. You should look at them and you should be aware of what they are. And even if you're not using neural nets, you can still use word embeddings. Okay? People forget that. They think, oh, I have to use neural nets if I'm using word embeddings. No, you don't. You can just use the features and stuff them into linear regression, etc. Still works and they're still good. Do you have enough features? What's missing? Why is it not working? You should look at the output. What do you see in the errors were? What's the bit of information that makes you decide it's wrong? Could you give that to the system in some way to try to work out whether it improves? Yeah, you can't do it for every single one, but look at 10, 20 and see what the distribution of these things actually are. Okay, thank you.